What if you put rocket engines on the Eiffel Tower? This question comes from absolutely nobody, because nobody sane would ask it. But we're going to answer it anyway. Imagine, for a moment, that someone woke up one morning, looked at the Eiffel Tower, and thought, this would make an excellent space vehicle. Maybe they'd had too much wine. Maybe they were an eccentric billionaire with too much money and not enough adult supervision. Regardless, the plan is set. We're strapping rocket engines to one of the most iconic landmarks in the world and launching it skyward. Let's start with the basics. The Eiffel Tower weighs around 10,100 metric tons. That's about the same as 100 blue whales or 5 Saturn V rockets. Unlike a rocket, however, the Eiffel Tower was not built to fly. It was built to stand in place, wave at tourists, and occasionally have someone propose marriage at its summit. It has zero aerodynamics, a lattice design that maximizes wind resistance, and the structural integrity of a very enthusiastic paperclip when launched vertically. But we'll get to that. To lift something this heavy off the ground, we'd need a lot of thrust. How much? Well, to overcome Earth's gravity, we need more upward force than the Eiffel Tower's weight. That means we need over 100 million newtons of thrust just to get it off the ground, and even more if we want it to move at any reasonable speed. For reference, the Space Shuttle's solid rocket boosters generated about 12.5 million newtons each. So, to lift the Eiffel Tower, we'd need roughly 8 or 9 of those. Imagine bolting 9 Space Shuttle boosters to the base of a delicate iron lattice. What could go wrong? Let's say, somehow, you do manage to attach the engines. You've reinforced the base, you've bribed every French official within 10 miles, and you've handed out safety goggles to everyone in Paris. The countdown begins. 3, 2, 1. The engines ignite. For a glorious fraction of a second, the Eiffel Tower does lift off the ground, and then physics happens. Remember, the Eiffel Tower was not designed to fly, let alone survive multi-million Newton forces of controlled explosion from below. The moment those engines fire, the structure experiences stresses in directions it was never meant to handle. The rivets start to shear, the lattice begins to buckle, and then the whole thing disintegrates mid-air, raining down thousands of flaming iron shards over a very surprised Paris. The top half of the tower, if it's lucky, might briefly continue its flight before turning end over end and crashing into the Seine like the world's fanciest lawn dart. But let's pretend that somehow the engineers of this bizarre venture are incredibly good. Maybe they've reinforced the entire structure with aerospace-grade titanium. Maybe they've enclosed the lattice to reduce drag and shape the tower into a more aerodynamic form, basically turning it into a shiny metal baguette with boosters. Now we run into a different problem: steering. Rocket flight isn't just about going up. You have to go straight and not yaw, pitch, or roll yourself into a fiery death spiral. Conventional rockets solve this with gimbaling engines, stabilizing fins, or even computer-controlled thrusters. The Eiffel Tower has none of these. It has elevators, viewing platforms, and a gift shop. So, our tower begins its ascent, and immediately veers off course. At the speeds we're talking about, even the tiniest imbalance would cause it to spin, tumble, and tear itself apart. From the ground, it might look beautiful, a sparkling corkscrew of Parisian iron spiraling into the atmosphere, with a trail of smoke and flaming baguettes behind it. But what if, and bear with me, we made it to space? Somehow, against all odds and basic engineering, the Eiffel Tower has escaped Earth's gravity. It's now in orbit. What then? Well, congratulations. You've just placed a 300-meter-tall monument into low Earth orbit with no way to slow it down, change direction, or do anything except float and pose dramatically. It would become one of the most massive and dangerous pieces of space debris ever launched. Within days, it could smash into satellites, tear through the ISS like a giant metallic toothpick, or slowly decay in orbit until it re-enters the atmosphere, giving the world a meteor shower shaped like Paris. And then there's the political fallout. France is now short one national landmark. Tourists are furious. The international community is very upset about the unexpected iron rain. NASA is trying to dodge the orbiting observation deck coming at them at 28,000 kilometers per hour. The UN drafts a strongly worded letter. Elon Musk tweets something cryptic. Eventually, the tower begins to re-enter Earth's atmosphere. Most of it burns up. But the lower sections, reinforced to withstand launch, make it all the way down. It lands in the Australian outback, creating a crater and a new tourist attraction, the inverted Eiffel. So, what have we learned? First, don't put rocket engines on national landmarks. Second, structural design matters. And third, just because you can imagine something doesn't mean you should strap boosters to it and light a match. Still, if you're determined to see the Eiffel Tower fly, there's a safer option. Build a scale model, attach fireworks, and launch it in a field, far from any major cities. Just make sure the top doesn't land in your neighbor's pool.